And also we have g pi equal g minus pi, periodic condition, because f is periodic. Now we consider the 2 pi periodic extension of g. Still we denote it by g. Then we have f minus g L2 square, L2 norm. The L2 norm, what's the L2 norm? L2 norm is the we have the inner product of f and g. That is 1 over pi minus pi fg. Then the norm, L2 norm is the square root of inner product which itself. Okay. I remember I have this introduced this in last set of lectures, but I remind you here. Maybe you are not very comfortable with this notation. Okay. So this by definition is the integral, maybe 1 over pi, or I write the pi there. I don't want to write the pi, so pi here, minus pi fx minus gx square dx. And this can be estimated below. Fx plus gx, fx minus gx, maybe fx minus gx dx. And the first term here, the first term will not greater than the supplement of the absolute value of f, because g is controlled by f. G is controlled by f here. And f, of course, is also controlled by the f itself. So this term will not greater than twice of the L infinity norm of f. So we can move this out and continue our estimate. So this will not greater than twice of the supplement of f on the interval. Maybe why should I write so complicated notation? I simply write twice of the L infinity norm. Then integral minus pi fx minus gx dx. And then we divided to use this property, we divided the integral from minus pi to pi by the integral over the small subintervals. Okay, so because we have the partition of the interval minus pi to pi, so the integral from minus pi to pi can be divided into the sum of the integral over every subinterval. Okay, so we do this. So this is precisely equal to 2, then sum I from 1 to m, xi minus 1 xi, then fx minus gx dx. But in the subinterval xi minus 1 xi, the supplement of f in this interval, f minus g, will not greater than omega I. So this implies this condition, this property implies that for x in xi minus 1 xi, fx minus gx will not greater than omega I. So using this property, we can replace this integrand by omega I. Then this sum is omega I multiplying the range of this integral delta xi. But this is less than epsilon square. By our requirement of the partition, okay? Here, we choose the partition having this property, okay? So the oscillation area is less than epsilon square divided by 1 plus twice of the supplement of f. The 1 here, the row of 1 here is to avoid the denominator to be 0. If f is identically 0, this is also allowed. But in that case, this the denominator is 0, meaningless. Therefore, we add an 1 here to save us. Okay. So using this result, this oscillation area multiplying the twice of the L infinity norm of f will not greater than epsilon square. So we obtain this result. This result means that the left-hand side is the L2 norm square of f minus g. Okay, so we have pi f minus g L2 norm square less than epsilon square, or f minus g L2 norm less than epsilon square root of pi. That's okay. Of course, this is less than epsilon because pi is greater than 1. Okay. Now, g is piecewise differentiable. So for g, because g is a piecewise linear function, it is piecewise differentiable. So we know that the Parseval identity for g is true. Parseval identity for g is true. So g is piecewise differentiable, actually piecewise linear. So Parseval identity is true for g. And so let Sg, S and G be the partial sum of g. Then partial sum of g we know that Parseval identity means the L2 norm of S and G minus G goes to 0. Why this goes to 0? Because recall that the L2 norm, the square of the L2 norm is, I don't want to square, S and G minus G L2 norm square is minus pi pi S and G minus G square. Okay, so this goes to 0 is equivalent to the Parseval identity. Why this is true? We have mentioned this before. The first line, the Parseval identity under this S and this is exactly the L2 norm of S n minus f. Okay, so Parseval identity is equivalent to the L2 convergence of Sn to f. Okay, although we will have not said this, but it is easy to see. You look at here. Parseval identity is precisely the right hand side goes to 0, but the right hand side goes to 0 is precisely the L2 norm of Sn minus f. L2 norm goes to 0. Okay, the left hand side is the L2 norm, the square of the L2 norm of Sn minus f. The right hand side goes to 0 is equivalent to Parseval identity, but this is equivalent to the L2 norm square goes to 0. Okay, so once you have Parseval identity, you have this L2 conversion. Okay, so now our G here, our G is piecewise differentiable. So we have proved that piecewise differentiable function, the Parseval identity is true. Therefore, for G, the L2 norm of the partial sum minus G goes to 0. Okay, so we have this result. Now, we have an important observation. The partial sum of F minus the partial sum of G is exactly the partial sum of F minus G. This is a key observation. So, using this observation, we see that by Bessel inequality, the Sn minus Sng, the partial sum, the L2 norm of the partial sum will not greater than the function itself, because F minus Sn minus Sng is the partial sum of F minus G. The L2 norm of the partial sum will never greater than the partial sum of the function. This is the Bessel inequality. Bessel inequality means that A0 square plus k from 1, ak square plus bk square not greater than pi minus pi f square. This is precisely the square of the L2 norm. So even if you sum from 1 to infinity, you will not greater than the L2 norm. But now you are partial sum, you only sum from k from 1 to n. Of course, it will not greater than the square of the partial the L2 norm. Okay, so this is the consequence of Parseval identity inequality. Okay, so we have Sn minus f square. By the triangle inequality, you can prove that for norms, like Euclidean space, for norms, for any kind of norms, triangle inequality is true. For all kind of norm, no matter L2 norm or Euclidean norm in Rn, or the L infinity norm we use to describe the uniformly convergency, triangle inequality remains true. Okay, so by triangle inequality, the L2 norm of Sn minus f will not greater than the L2 norm of Sn minus Sng, then plus Sn G minus G, then plus G minus F. This is triangle inequality. Although we have not proved this, but it is not difficult. By this equality here, we obtain that this will not greater than twice of f minus g L2 norm plus Sn g minus g L2 norm. But f minus g, the L2 norm of f minus g is less than epsilon. Okay, our g is chosen in that where is our g? Our g by this estimate, our g, let's check where is our g. G is the piecewise linear function. Yes, we estimate here, right? The L2 norm of f minus g is less than epsilon. We obtained this result before. Okay, this is not easy to obtain. We estimate the integral of f minus g square in minus pi integral. Then by a somewhat long computation estimate, we reach this result. Then this implies that the L2 norm of f minus g is not greater than epsilon. Okay, so why we need this? Now it is time for us to use this result. So this is not greater than 2 epsilon plus Sn g minus g2. Okay, now we're taking limit. Let n goes to infinity. Let n goes to infinity. Taking supplement limit. Then Sn minus f square not greater than epsilon. Maybe I will write more clearly. 2 epsilon plus Sn g minus g. But this goes to 0. Because for g, we have Parseval identity. Parseval identity means that the partial sum converts to g in L2, or the L2 norm of the difference goes to 0. We mentioned this here. Okay, so the L2 norm of Sn g minus g goes to 0. So when you take the supplement limit here, the two terms inside, one is the constant, the other goes to 0. So the supplement limit will not greater than 2 epsilon. This is true for every epsilon. So let epsilon goes to 0. Let epsilon goes to 0. You obtain that the limit supplement is 0. The non-negative sequence for this non-negative sequence, its limit supplement is 0, implies that it converts to 0. So we conclude that Sn goes to 0. Okay, but this is equivalent to Parseval identity. Go back to C again. We mentioned this many pages ago. Here, if the L2 norm of Sn minus f goes to 0, that is the left-hand side goes to 0. The left-hand side goes to 0. The right-hand side must also goes to 0. But the right-hand side goes to 0 is precisely the Parseval identity. Okay, so once we have this, once we obtain this result, we obtain the Parseval identity. So we have proved the Parseval identity for Riemannian integrable function. Okay, we consider the case that f is integrable. For this case, we are done. We complete.